So starting with number 5, and you'll note that it says that you can use a graphing calculator whenever helpful on any of these. So for number 5, it tells us that the acceleration of a particle moving on a straight line is a equals cosine t, and at t equals 0, the particle is at rest, so velocity 0. We want to know the distance it covers. That's a poor wording. From t equals 0 to t equals 2. All right. So in order to do this, we've got to figure out a position function for it, which means that first we need to figure out a velocity function for it. So first, to find velocity, we'll just integrate acceleration. So our v should be the integral of cosine of t. Integral of cosine ought to just be sine of t plus a constant. And we know that when t equals 0, v equals 0. So 0 equals 0 plus c, so that constant is a 0. So our velocity function should just be sine of t. In order to figure out the distance that it covers. Well, the good news is, since we're talking from t equals 0 to t equals 2, sine is always positive from t equals 0 to t equals 2. It's always positive from 0 to pi. So in order to figure out the total distance that it covers, all we have to do is just integrate from 0 to 2 the sine of t dt, which ought to be integral of sine is negative cosine. So negative cosine of 2 minus negative cosine of 0. Cosine of 0 is 1, so negative 1 is positive 1. We end up with 1 minus the cosine of 2, which looks like that's choice B. Any questions or issues there with number 5? All right. Next one after number 5 is number 20. Maybe if my pen will write. There we go, number 20. So, page here. We are assuming that the density of vehicles during morning rush hour, the number of vehicles per mile, for a 20-mile stretch of highway with a bunch of names in it that we don't really care about, is given by f of x. So our density is f of x, and x is distance in miles. We want something that gives us the total number of vehicles from the bridge to the point x miles south of the bridge. So the only thing that we need to do here is just integrate it. I mean, we're just looking at an integral from 0 to however many miles south we are of the function that represents the number of cars per mile, f of t dt. I mean, that's literally all that number 20 is. It's just an integral from position of 0 miles south to x miles south of the bridge of the density of the cars, which is in number of cars per mile. So if we integrate number of cars per mile, we just get a number of cars. So that's all it is. The 20 doesn't need to get plugged in because we're utilizing that 20 along this stretch. X is going to be some value between 0 and 20. that make sense to everybody for 20? Next one is 21. So for 21, we've got the center of the city. We're assuming the city is a circle, so let's draw a circle. And the center of the city is on a straight highway with a radius of 3. The density of the population is thousands of people per square mile, so our density is f of r equals 12 minus 2r at a distance r miles from the highway. And so we want to figure out a formula to represent the population of the city. Okay, that's a fun one. All right, so we should be able to represent, let's see, we should be able to represent any distance away from the highway. So like, let's just call it some line going across here, right? Suppose we're here, we're the same distance from the highway at any vertical piece away from here. And so we should be able to figure out what this distance is from here, from the center of the circle out. Let's see here. That's 3. How do they define this? This is a distance r. That's annoying that they're going to call that r. This is r miles from the highway. And so let's see. Yeah, so let's say at this distance, we should be able to figure out its length. So this length here should be, let's see, this will be the square root of 9 minus r squared. And so the entire length of this like strip of city, this r distance away, should be 2 times the square root of 9 minus r squared. And so it's got a infinitesimally thin thickness here of dr. And so we should be able to take the length of this and multiply it by the density of the city, which is 12 minus 2r. So density times the area, when you sum together all of those, should give you a total number of things, in this case, number of people. And so we take the 2 times the 12 minus 2r times the root 9 minus r squared times the dr and integrate it from 0, or 0 distance away from the highway, all the way up to the furthest distance away we could be, which would be 3. And then from there, we just figure, we just get an answer. Good or no? Is that one of the answer choices, hopefully?
Yeah. So why can't you just integrate the density function? Why do you have to like multiply stuff to it?
Well, because the density represents the density at a point. So like the density is, at this point, the density is 12 minus 2r. At this point, the density is also 12 minus 2r. But I have a lot of these densities of 12 minus 2r going across this line. I have 2 times the square root of 9 minus r squared of them.
So in the last problem, when it was also dealing with density, like it also gave us a density function. Why didn't we have to do like extraneous stuff there, but we do here?
On the previous one you're talking about?
Yeah, when it said like the density of the vehicles is blah, blah, blah.
Well, yeah, so for that one it was along a strip of road, so it was in like a single dimension. So the density along this strip of, well, we'll just say from here to here over this 20 miles, right? The density at any point along here was whatever the function was, f of t. But here it's the density along this strip, but this, each strip is different. So we have to find the total number of cars in each strip and then sum them all together, which is what we've done here. We found the total number of cars in each strip and then sum them together. Here, it's just density of cars at each instant going along the highway. So you sum all of those together from 0 to 20 if you want the full 20, or from 0 to whatever value you.
So is that choice B?
I don't know. Let's see.
Because on the answer key.
Oh, yeah. Okay. Oh, so
yeah.
It should be C because, well, what do we do here? We did from 0 to 3, right? From 0 to 3 gives us half of the city. So we got to multiply this by 2.
Oh, okay. That makes sense. All right. Thank you. Thank you.
Okay. Sorry about that. I forgot about the other half of the city. Probably shouldn't do that. Any other questions on 21? A lot of people were asking about 21. So. All right, 22. Oh, another one of these fun population densities. This time we got a chart. We got the population density of Winnipeg. Let's see. Given a chart using a Riemann sum, we can calculate the population living within a 10-mile radius of this center to be approximately, what is this? This is distance from the center of town as it increases. Okay. So let's see, does it say yeah, it doesn't specifically say which type of Riemann sum to use, does it? Unless I'm misreading it.
No, it doesn't.
It doesn't. Okay, that's annoying. I suppose if we wanted to, since it is it doesn't even say like, yeah, that's a bad question. There's no way to determine which type of Riemann sum they'd want you to use. So let's just, I don't know, let's just use a left one, since why not? We could use a left one. I don't know. I guess that would make the most sense to use a left one, because we know that this function is decreasing. And so that's going to give us an overestimate. So if we're like, trying to figure out something with the city and how to use money or whatever, I don't know, it'd probably be best to overshoot the amount that you need by thinking you have more people than undershoot it by thinking you have less people. So let's use a left Riemann sum here. So the distance in miles from the center. So what we're looking at here then is our city, and in the distance, so depending on what the radius of the circle in which you are in, as you spread out from the center of the circle, that should give you the total number of people in each ring if you can multiply the distance by the circumference of this circle. So our circumference of each circle ought to be 2 pi r. And so if I take the total number of units of this circumference and multiply it by the density of the people in it, which is our function, what they call it, f of x. So if we take 2 pi r times f of x, that ought to tell us the total number of people in each ring, and we just need to sum together all of those using our integral from 0 to 10. And we'll, like we said, use the approximation method for this. So the first term that we should get using a left Riemann approximation should be a height of, our distance. If our r value is 0 miles from the center, we ought to get 0 times the length of that interval, which is 2, times the value of our density, which is 50 from the chart. And then for the second one, we should get 2. Oh, sorry, I forgot my 2 pi in there. We should get 2 times our 2 pi times our r value, which is 2, times our height, which is 45. And for the next one, we should get our 2 pi times our 2 again, because the length of the interval is 2, times our r value, which is 4, times our height of that one, which is 40. And then the next one should be 2 pi times that same 2 again, times 6, which is our r value, times 30. And the next one should be that same 2 pi times our 2, times our 8 this time, times our 15. And if you were to add all of those things together, I don't know what it would come out to be, but it would come out to be something. What would that come out to be? Let's see. They've all got a 4 pi in them, right? So this one's 180, this one's 20, that's 300, 460, and 90 would make 550. So 550 times 4 pi. This one's 0. What is 550 times 4 pi?
It says 6,911, which is not an answer choice.
Okay, yeah, so that probably shouldn't be an answer choice because it does say that the units are in hundreds of people. So we'll add a couple zeros to that, and that probably comes pretty darn close to one of our answer choices since it's an approximation, I hope. Yep, I'd go with choice C. Good or no?
For this one again, like you can't just do a regular Riemann sum. You got to throw in the 2 pi r to it.
Yep.
Is that because
this is density, and so density times the size of the thing that you're looking at the density of gives you the number of people, and then you're summing together those from 0 to 10.
Okay.
Once again, it's density of a ring. This one was density of a slice. This one was density at a point. So this one just got to stay as integral of the density. This one had to be integral of the number of people in that slice. This had to be integral of the number of people in that ring. Does that make sense to everybody or no?
Yeah.
All right. Next one, 25. 25. How long will it take to release 9 tons of pollutant if the rate at which the pollutant is being released is TE to the negative 0.3 T? So let's see. It's the rate at which it is being released is that. So we just want the integral. Basically, for this one, we're just going to look for an integral from 0 to, I don't know, some value x that we're looking for. of t e to the negative 0.3 t dt, because the, that should represent how much of it has been released from 0 till some x value. We just want that to equal 9. And so let's see here, how are we gonna, I mean, I would just, if I were me, I would just graph each of those things in your graphing calculator, and then see where they equal each other. You can graph the integral from 0 to x of that function.
Yeah, I tried graphing it, but it was taking like 10 minutes for my calculator to load, and it like never produced a graph. And it's done that for the other integral things that we have to do this for too. So I don't know how else I could get a graph if it takes like 10 minutes.
Yeah, the only other way to do that would be to integrate this expression, which is not something that you are able to do. So if, I mean, I wouldn't imagine that they're going to give you anything where you have to graph this integral and then solve it, because it does take a long time on your graphing calculator if you're not just using Desmos or something. So
okay.
You would either be able to integrate that and write out an expression that was nice and easy, or you would not have to solve it. They just tell you to write it.
Okay.
So I don't know what that comes out to be offhand, but that's the only real options. Graph it, learn to integrate by parts, which you're not going to do because you don't need to till Calc 2, or leave it like this. I mean, and that's how they'd have you leave it on the AP test, probably.
Okay, thank you.
Yep. Any other questions there on 25? Everybody see why that's the right setup?
Yeah.
Okay. Let's see here. Next one is 31. So for 31, we've got an 18-wheeler traveling at a speed of v miles per hour. Going v miles per hour. It gets 4 plus 0.01 v miles per gallon gas mileage. Its speed is 80 times t plus 1 over t plus 2. And we want to know the amount in gallons of diesel fuel used during the first 2 hours. So how much fuel does it use in 2 hours? So what are okay? They give us just regular old numerical answer choices for this, right? So we should be able to set this up as an integral. We should, let's see here. Let's think about this. If it's getting 4 plus 0.01 v, write this out. 4 plus 0.01 v, that's miles per gallon. We should be able to figure out how many gallons it takes to go 1 mile. So we should just be able to flip this thing over and say that it goes 1 over 4 plus 0.01 v, or it takes 1 over 4 plus 0.01 v gallons to go each mile. And so if we have a value for gallons per mile, we should be able to, let's see, if we can take, let's see if we can make these units work out nicely. Our speed, which is in miles per hour. we should just be able to figure out that its total distance traveled, right? Whatever its distance that it's traveling is going to be whatever its velocity is, times the change in the time period. And so that should tell us then that if we want to take gallons per mile, 1/4 plus 0.01 V, gallons per mile, times miles, that should be times V times delta T. And our delta T ought to just be our dt for our change in time. So really we've got V over 4 plus 0.01 V dt. Everybody good with that so far?
Did you just use velocity equals distance over time and then like?
Yeah. Yep.
Oh, okay.
And I wouldn't expect them to give you one that's this complicated to set up, but that's fine. It's still good practice for us. And so now we've got two V's in here. We need to integrate though with respect to T with these T values. So we got to turn the V's into terms of T. And we know that V is 80 times T plus 1 over T plus 2. So we should do from 0 to 2, and I'm going to have an 80 times T plus 1 over T plus 2, all over 4 plus 0.01 times 80 times T plus 1 over T plus 2 dt. And that should give you the total number of gallons of fuel that it uses in those 2 hours. So I don't know what that comes out to be, but it comes out to be something.
So because they gave us the speed, do we not have to do absolute value for the velocity, since speed is like that is a scalar and not a vector?
Yeah, exactly.
Okay.
I don't know what that integral come out to be. Could simplify the integral down if we wanted to. Make it easier to type into our calculator, but get rid of the T plus 2's if we want to by putting this times T plus 2. So we've got 80 times T plus 1 over 4T plus 8 and then 0.01. Let's see, 4T plus 8, and then this should be 0.8T plus 0.8. So if you want to simplify that integral down a little bit more, you could take the 80 out of it if we wanted, and make this an integral from 0 to 2 T plus 1 over 4.8 T plus 8.8. That's easier to type into your calculator at least. What does that come out to be?
I got 23.1, which is answer choice C.
Wonderful. Hopefully that's what it said the answer was. Any other questions on that one? That one's also more complicated than I would expect you to see.
With these packets in general, are they generally like good guides to what would be on like AP multiple choice besides these challenge problems? Or
yeah, I mean, if you're looking at the non-challenge problems, I would say yes. The challenge problems are generally more difficult.
Okay.
Even some of the regular problems are just a little bit more difficult, I would say also, but not all of them. You know, some are good and some are less good, but overall, yeah, if you're not looking at the challenge problems and you can do most of these, you're probably fine. Even if there's some that you struggle with, you're probably fine. All right. Let's see here. Next one is 14. 14. Current world population is 6 billion. And they're giving us a formula to represent how much it's going to increase. Let's see. We want to know what the average population of the world in billions over the next 25 years would be. So if we're just looking for an average population, we just need to take our, we can find, let's see, the current world population is 6 billion. The population T years from now is estimated to be. Okay, yeah, so the integral from 0 to 25 ought to tell us how many people at each t value, whatever t value we, you know, if we go from 0 to 20, it should tell us how many people there are 20 years from now. If I go 0 to 25, it should tell us the total population 25 years from now. So we're going to do 0 to 25 of that population function, which was, I'm just going to write capital P of t. And since we're looking for an average, we got to do 1 over 25 minus 0 out in front of it. And that's really all that that one should be. And I don't know what it comes out to be. What does that come out to be?
Looks like 8.221.
8.221?
Yes.
So I guess choice D, 8.2 billion. This is the population at any value. So this is the total population at 25 years divided by the 25 years.
So the 6 billion given up front was like completely unnecessary to include at all.
Correct. Did not need that at all. Other than, I mean, that's where the 6 coefficient on the e to the negative 0.024 comes from. So at t equals 0, you got 6 times e to the 0, which is 6 billion people. That's why there's a 6 there. But it's, other than that, it's not required to do anything with the problem itself. All right, 16. We've got a stone is thrown upward from the ground. We are given its initial velocity. And we want to find the average velocity. So in order to figure that out, let's see, we just need to figure out a function for the velocity. So if a of t is negative 32, then v of t ought to be negative 32 t plus some constant, and it said our initial velocity was 96, so 96 equals 0 plus c. C equals 96, so our velocity function should be negative 32t plus 96. And if we want the average velocity in the first 2 seconds, it ought to be 1 over 2 minus 0 times the integral from 0 to 2 of negative 32t plus 96, which ought to be, let's see, half of negative 16 t squared plus 96 t from 0 to 2, which, what does that come out to be? Negative 64 plus 192, which is half of 128. So 64 I assume it is feet per second based on our accelerations.
Yeah.
Everybody good there with 16? Any questions on 16?
Nope.
All right. Let's see what else we got here. 21, we've already done. 26. All right, 26, the total area bounded by the curve x cubed minus 4x squared plus 3x and the x-axis. So first off, I'm going to figure out where this has x-intercepts. So x, and then I will factor this into x minus 1 and x minus 3. So I know this has x-intercepts at 0, we'll just do it this way, at 0, 1, and 3. And if I want to figure out when this is above the x-axis and when it's below the x-axis, we can just plug in values. If I plug in a -1, I get a negative times a negative times a negative, which is a negative, so I'm below the x-axis. And then, so I'll sort of draw it like this, and then from 0 to 1, if I plug in like a half, I get a positive, a negative, and a negative, which means I'm now above the x-axis. And then between 1 and 3, like 2, I'm going to get a positive, and a negative, which means I'm negative, so I'm now below the x-axis. And something greater than 3, like 4, it's going to be positive, 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 and I'll now be back above the x-axis. So I know that the region that I'm looking for here should be the region between 0 and 1 and between 1 and 3, because the rest of this stuff is all the unbounded stuff that it's not talking about. It says the total area bounded by them, so that's 0 to 1. And then 0 to 1 is above the x-axis, that can stay positive. We will subtract the stuff that is below the x-axis. Because it comes out to be a negative, and then your calculator will approximate that integral for you because it looks like they gave you all your answers in decimals. So,
yeah, I got the same equation, but I kept getting 3.083, but the answer they got was 3.
Yeah,
I did the same thing. Yeah.
It like gives
The
you
answer is-
exactly 3.083, but they give it as 3, which is ridiculous.
26, let's see. Yep. As I flipped back here to like their answers and like they write out what they did sometimes. They said is approximately equal to 3.083. So that should definitely be choice E. I don't know why unless it said it didn't say around it anything. So yeah, it should be E. It should be 3.083. I don't know what to tell you about that.
Okay.
That one, I think I need to adjust the answer key on. Yeah, I mean, yeah, definitely. All right. Next one is 15. All right, 15. A beach opens at 8 a.m. and people arrive at the beach. We got a rate 10 plus 40t. assuming no one leaves before noon, at what time will there be 100 people there? So no one's leaving. Beach opens at 8, so we assume there's no one there at 8. And we need to integrate. We'll just integrate this from 0 to, I don't know, x of 10 plus 40 t dt to figure out when that equals 100. And our integral should be 10x plus, that should be 20t squared, so 20x squared minus 0 equals 100. And we should just then be solving 20x squared plus 10x minus 100 equals 0. And let's see, we could divide a 10 out of all of that. 2x squared plus x minus 10 equals 0. And let's see, yep, that should factor. So it looks like that should factor to a 5 and a 2 here. What is that? Plus and a minus. So x equals negative 5/2, so that wouldn't make sense. Or x equals 2 hours after it opened, which would be, I don't know, when did the beach open? 8 a.m., so it must be 10 a.m. Choice B. Everybody good there with 15? Any questions on 15? All right, 25, 31, we've done, 21, we've done, 22, we've done, 31, 21, 22, still done all of those. 25 and 26, we've done. Any other questions? Looks like we've done everything that anybody's asked for.
Can you do 29?
29, sure. Let's see here, 29. Okay, we got some graph for 29. Let's see, just sort of sketch this. Something like that. Going to 8 and going up to 300 here. And what is this? The website went live at noon. The rate of its number of visitors per hour. So this is a rate function. This is R of t. We'll call it. We want to know approximately when did the 200th visitor go to the site. So we just want to know when does the integral from 0 to some t value of our rate function. We want to know when does that equal 200. 200, right? Is that what I said? And kind of just got to look at that and estimate about when you think that that area underneath there is going to have reached about 200. And I don't know. I mean, maybe a trapezoidal rule would be good to try and figure that out. Let's do, just to get pretty close. Well, actually, let's I don't know, let's just use a left Riemann sum. We know that this is always increasing, so a left Riemann sum should under approximate it. So when we get to 200, we know that it's a little less than what it took us to actually get to 200. So that first one looks like it's maybe about 10. If I just do a left, or sorry, the first one is 0. The second one, if I go, let's do a midpoint. Let's do a midpoint. If I do the midpoint of 0 and 1, that's probably about 5. So we'll call that 5 times the length of 1. Let's do the midpoint of 1 and 2. Looks like that one's about 25-ish. So that'll be plus 25 times the length of 1. The midpoint of 2 and 3 looks like it's about 70. So that's about 100 right there. The midpoint of 3 and 4 looks like it's 100 and 20 something or another. So looks like it should be sometime between hours 3 and 4. So this is hour 1, this is hour 2, this is at the end of hour 3, at the end of hour 4, we're going to be over 200. Does that make sense?
Yeah, thank you.
Uh-huh. All right. Any other questions?